This is sections 3.2, 3.3, and 3.4. This is part 2 of chapter 3. So as a reminder, if we already know that lines are parallel, as it's been stated already for us, we can use the postulates and theorems to say that angles are congruent or supplementary. But if we see that angles are congruent or supplementary, we can use the converses to prove the lines are parallel. So this whole lesson is going to be about proofs and additional postulates and theorems that we can use to prove more things about lines and their angle relationships. The first two are going to be the perpendicular transversal theorem and its converse. So the perpendicular transversal theorem is saying if a line is perpendicular to one of a set of parallel lines, then it's automatically perpendicular to the other. So if I knew H is parallel to K, and I know that J is perpendicular to H, then I can say that J is perpendicular to K. The converse is going to say if two lines are perpendicular to the same line, they're parallel to each other. So in this case, if I knew that J was perpendicular to H and I knew J was perpendicular to K, then I can say that H is parallel to K. So what's nice here is we're still using the converse to make a statement about lines being parallel. And the theorem is not saying lines are parallel. Theorem, we already knew the lines are parallel and we're proving something else. The converse, we're trying to prove that the lines are parallel to each other. And then we have one more last reason we're going to learn, and you do have to say the full name for this one. So it is the transitive property of parallel lines. You cannot just call it the transitive property, so we're going to call it the transitive property of parallel lines. So that's if two lines are parallel to the same line, they're parallel to each other. So if I knew that A was parallel to B, and I knew that B was parallel to C, then I can say that A is parallel to C. So this is the only time we're using something that doesn't have the word converse in it to state that two lines are parallel. So let's get into it. Example 1. Remember, our first step is to make sure everything that was given to us is marked as given. They already have given written as the reason for number 1, but I see that there are two givens up here, that P is parallel to Q, and that angle 8 and angle 7 are a linear pair, which is here at step 4. So I'm going to fill that in as given as well. And now, if I know the lines are parallel, I could say that angle 1 and angle 8 are congruent based on the relationship here of being corresponding. So this would be the corresponding angle postulate. If you call it theorem, that's fine. The words are mostly interchangeable for our purposes. It's okay. Now, we're going from these two angles being congruent to these two angles being equal. And remember, that is our definition of congruence when we switch the symbols. Now we have that these two angles are a linear pair. So this is going to be back from chapter 1. If you know that angles are a linear pair, you can call them supplementary by the linear pair postulate. If you recall, I also told you anytime you saw a word, you would likely use the definition of that word. This is one of the instances that is not true. So I'm seeing the word linear pair. I'm not going to use the definition of a linear pair because that's just talking about them being adjacent and forming a line. That's not saying they're supplementary. So when I see the words linear pair in a proof, I can automatically use the linear pair postulate to say that they're supplementary. Now I see a word that they're supplementary, and in the next step, I see that the sum of their measures is equal to 180. And that is exactly what it means to be supplementary. So we're going to call that the definition of supplementary. So my next step, it looks very much like step 6, right? I have, instead of 8 plus 7 is 180, I have 1 plus 7 is 180. And up here, 1 and 8 were the same thing. So I'm replacing the 8 with a 1. That is substitution. And then my last step, I'm calling angle 1 and angle 7 supplementary. So the only reason I'm able to call them supplementary is because I knew that they added to 180. That is also the definition of supplementary. And I know I also mentioned this to you, that usually it's going to happen immediately after, that if you see a word, after it will be the definition, but occasionally it'll be in the reason of the statement we are using the word. And that is our proof for example 1. Let's try a few more together. So example 2, we have two things that are given to us. Angle 1 is congruent to angle 2 here at step 1. And segment JL is perpendicular to segment LM here in step 3. So step 2 has the fact that JL is going to be parallel to KM. And if I knew that 1 and 2 were congruent, and now I'm able to say that lines are parallel, it's going to be because of the fact that 1 and 2 were congruent. So if I look at the lines that I'm talking about being parallel and I draw that common transversal between them, these angles are between the lines and on opposite sides. So they're alternate interior angles. So we'll use the alternate interior angle converse because we are proving lines parallel. We already talked about 3 being given, so now step 4. I'm saying that these two segments are perpendicular to each other. They're perpendicular to each other because I knew that JL was parallel to KM and JL was perpendicular to LM. That means KM must also be perpendicular to LM. And that was the perpendicular transversal theorem. And I know it's the theorem and not the converse because I'm not talking about lines being parallel here. And our third example, before you try one on your own, is a longer one. It has quite a few things that we have talked about in chapters 1 and 2. So I'm going to fill in my givens. I have the fact that these two are 53 and 48. And I also have that angle BEF is 79 degrees. That's down here in step 7. All right, so step 2. Step 2 has nothing to do with step 1. I don't see those numbers appearing again. I see a CBE that wasn't even here. So if I look at the picture and I say CBE is equal to CBF, this one here, plus FBE, this one here, I'm saying this big angle is equal to the sum of the two smaller angles. That is the angle addition postulate. And now I have the CBE again, but now I have the numbers plugged in. So I turned CBF into 53. I turned FBE into 48. I have never seen an equation before with 53 plus 48 in it, so I know it's not transitive, but I did take an equation that existed and replaced parts of it, so it is substitution. And the next step, again, looks very much like 3, except instead of having separate numbers of 53 and 48, they're added together. And remember, that's not the addition property, that is simplify, because we didn't do something to both sides, we just combined our like terms. Here's one we haven't seen in a bit, but the measure of angle BEF is equal to the measure of angle BEF. So I'm looking at the same thing on both sides of this equation, like looking at a reflection. So that's the reflexive property. All right, this one can be tricky. So I've already had an equation with a 101 in it, step 4. So the 101 is there, and the other side of the equation was CBE. Both sides now have plus the measure of angle BEF to them. So what we've done is we've added the same exact thing to both sides of a previous equation. So that is the addition property. All right, when you add the same thing to both sides of an equation, it's the addition property. And then we had our given that the measure of angle BEF is 79. And now step 8 looks a lot like 6. I still have the 101. I still have angle CBE. I still have angle BEF. But now this angle BEF has turned into a 79 degrees because they were equal. So this is going to be another substitution. And much like happened in step 4, we went from 2 numbers being over here to just 1 because they were combined. So that is simplify. So if these two angles add to 180, I can now call those two angles supplementary. So that is the definition of supplementary. And our last step here is calling two lines parallel. So when we're calling two lines parallel, if it wasn't given, we're always going to look at the step immediately before it to determine our reason of why. And if I look at my picture, the location of the two angles we're talking about, angle CBE, oh, that's not working for me. Let's try CBE and BEF. So if I look at where these two angles are, they're between the lines I'm saying are parallel, and they're on the same side of the transversal. So that is the consecutive interior angle converse. Again, converse because we said that the lines are parallel. So here's one for you to try. Pause it if you'd like, and the answers are posted online. All right, just like before, we are going to write one from scratch. We are given two pieces of information. I'm going to set up my columns. All right, statements and reasons. So I'm going to start with just one piece of information. I'm going to start with A being parallel to B. That's given. I'm ultimately trying to prove that C is parallel to D. So I'm trying to find one angle on C and one angle on D to compare to each other. But right now, the only angles I can compare are ones on A and B. So I could either cover up line C and look at the two angles on line D that are both A and B, or I can cover up line D and do the same thing. And that's actually going to be the easier way for me, because this is an easier relationship to deal with than that one would have been. So knowing that A and B are parallel, I could say that 1 and 3 are congruent because they're alternate interior angles. So that's going to be the alternate interior angle theorem. Because again, we're not saying the lines are parallel, we're saying the angles are congruent. We already knew the lines are parallel. I'm going to now throw my other given in. And if I look at what I've written in my proof now, I have two different lines and both of them contain angle 3 in them. So I can actually link together 1 and 2 by the fact that they have angle 3 in common. So we can go to say angle 1 is congruent to angle 2 by the transitive property. If you want to go wild and call it the transitive property of congruence, that's fine. And now that I know angle 1 and 2 are congruent, I do see that they're on a common line A, which means that C and D are now eligible to be called parallel, and I'm going to do that. So C is parallel to D. That's what we wanted to prove. And these angles are one outside, one inside, so that is corresponding. They're in the same position. And because we're calling them parallel, we're going to use the converse instead of the postulate. So there's one last problem for you to try. Pause it if you'd like. Answers are posted online. Otherwise, that is the end of part 2 of chapter 3.